Okay, we actually finished the planning portion and trajectory planning, and this week we still have two more weeks to finish. And then at this moment, I would suggest that to try to get things done as early as possible. Don't pile up things until the last minute. And usually, it's very difficult to finish a lot of things in the last week, okay, or last few days. So try to finish it early, okay? Okay, that's what I can suggest. And if no question, any question about the homework or other things?
Yeah, actually, I do have a question. From assignment 4, I was
Okay.
having, I was looking back on that one, and I'm still having issues with it, and I was wondering if you could go over it again.
Number 4.
Yes.
Actually, number 4, I would say the programming assignment for number 4, almost nobody is correct, okay? Probably there's only one student who is correct on that one, but I mean, most of the students get it wrong, okay? First thing is like, this one is a spherical robot, okay? So let's see here, if you just look at the first, okay, just look at this point. Just look at this point. And then there's one revolution, and it's over here. So this point, you actually make a rotation, it will be a circle, right? That should be a circle. So based on that, before you work on the second joint, the first one, it is a variable joint. And no matter what it is, let's assume that here you do have a point. And then this one, it rotates for the whole circle. There's a theta. It keep rotating. Okay, so it's a certain point, and it's not touching the ground. It actually, if you look at it, it actually is just a point, make rotation, and it will actually go through a certain circle. Okay, go through a certain circle. So that one is a circle, equation of a circle. Now, next one right here, at this point, you do have the second joint that also travel a circle. So if you cut this plane, it make another circle here. But this circle actually is what? Perpendicular to the first circle. So the first circle is like this. This one, if you cut, it actually perpendicular to it. So if you look at this one, and this circle travel around for the whole circle, so it basically will create a donut-shaped, it's like a pipe go around, and it will be a donut-shaped object. Only surface. Surface. Is okay? It's a donut-shaped surface. Inside here, inside the pipe, you can never reach it, because this point is only making a circle on the circle. Is that okay so far?
So far, yeah.
Yeah. So that's the answer. You need to describe this circle for all the point on here, right? Or all the point on here. So basically, let's assume that okay, let's actually take out these different things here, okay? So how to describe this whole thing? Let's assume that we actually just look at the location of this one. Location of this point here, right? It's right here. So this is G iteration, right? So G iteration, you have a fixed number. Okay, no matter what it is, this number is fixed. So it's actually, there is a Z0 that will be fixed. Okay, and the point on here, that's this arm actually is R, the radius. So the coordinate of this guy should be R times cosine theta 1. Okay, R sine theta 1 plus G. Okay, so that's the XYZ of this point. Right? So far, okay.
I think so.
And then after that, you need to add your no matter what XYZ you have from here to here to this point, and that's it. Okay. Actually, that's it. Okay, now let's look at how to calculate the XYZ differences. Okay, XYZ differences. So here, let's see. This one, let me take a picture. Okay, let me take a picture. So this one, you need to calculate the XYZ relationship with it. And then once you get the XYZ relationship, you can use the XYZ to generate the chart, okay, the workspace, and you can make drawings. Now let me actually clear this one. So as I said here, you do have a point, and this point travel on a circle that we know, we already described it. Now right here, how much your G, the smaller circle, the circling around is the surface. Okay, so for this circle, let's assume that here you do have a theta 2. And this is smaller r, okay, smaller radius. Let's actually call it smaller r. Okay, smaller r. So your z change. Okay, let's actually look at your z change. Your z change right here. This one theta 2. So this is g. The point over here, this g change, delta g. Delta g should be the same, all the same, no matter where you are. You only related to the theta 2. Okay, no matter where it is, it may be going this way, the same. Okay, we don't know, we don't care. There's a theta 2 you need to take care of. Okay, so that actually is a theta, delta G would be equal to R sine theta 2. So basically, you have the G naught plus R sine theta 2. That's your G. That's your eventual G should be. Your final G should be here. This one, you do have G naught. So G naught plus delta G, you get the G. Okay. And delta G equals this. So G portion is subbed. Okay, G portion is subbed. Now, this portion is right here. It will be affecting the XY because what? Here is in this direction. If you go to the middle here, okay, let's assume that you rotate to here, and it's cutting through here, right? Then your XY should be here. Okay, you see that to affecting both XY. So the length over here, this one actually is called, let's call it delta D. So delta D will be equals R times cosine theta, right? R times cosine theta. So R times cosine theta, that's the point. That's actually is the change on on a circle. So basically this one affecting your X and Y. Okay, this one affecting your X and Y. So that's actually make a copy for this one. One more time, let me actually copy this one. Okay, let me actually kind of clean it. Okay, now let's actually look at the circle. Now you do have a circle. And I'm for this one now, I'm actually looking at the top view. Okay, top view from the top to look at it. So I do have the circle here. I'm rotating here, right? This is a big R. This is big R, right? And at a certain point, you do have here, right? And your delta D is always here. Delta D is this much. Delta D doesn't change. Okay, delta D is the one that we calculate. Theta 2. Delta T actually is this amount right here. Delta T is this amount is actually is small r times cosine theta 2. Okay, so this one actually small r is over here, and this is theta 2. So this one is small r times cosine theta 2. Okay, and you go here to here. So right here, there's another angle here. This one is theta. This one is also theta. So the delta x portion, the exchange portion, should be the delta D times the theta cosine theta 1. It will be equal small r times cosine theta 2 times cosine theta 1. Okay, and this is a delta y portion. Delta y portion will be equals delta D times cosine theta 1. I'm sorry, this one is sine theta 1. Sine theta 1, it should be r cosine theta 2 times sine theta 1. Okay, now with this we get the answer. So with this we get the answer. So your eventual XYZ location should be equals okay, your here this one is your base x. Your base x is big R cosine theta 1 plus small r let's see, sine theta 2 times cosine theta 1. Okay, that's your x plus your y. Y is r sine theta 1 times small r. I'm sorry, plus small r cosine theta 2 sine theta 1. Okay, this one we calculated. It's actually from right here. And your g is your g dot plus b sine theta 2. That's it. Any question? That's the way to solve this location. Okay. Okay, let me actually clean this whole thing up. Let me clean this whole thing up. Okay. So we calculated, let me clean this whole thing up. Okay. So here we do have a circle. Okay. And to the ground. So the height, okay, it actually is on the surface, and here from the middle to the bottom. This height actually is called Z naught. It's a fixed size. Okay. It's a fixed size. Okay. And the bigger radius is R. That is also a fixed size. Okay, so the point over here should be, this point is the one that makes a circle. So that one is called S1, Y1, G1. It should be equals big R cosine theta 1, big R sine theta 1 plus G naught. Okay. I'm sorry, there's no plus. Okay, it's 3 coordinates. So R cosine theta 1, R sine theta 1, and G naught. G naught is how high it is. Okay. So that is the center of your pipe. Your pipe is over here, right? And then any point on your surface right here, that's also this is S2, Y2, G2. Okay, the points, the coordinate should be the change in G. Change in G is actually delta D. Delta D, as we say, it actually is small r times sine theta 2. So here, right here, this one G2 should be equals G naught plus R sine theta 2. Okay, so this is G2 is like this. Okay, then your S2 should be this one plus the delta D plus the delta T times delta D times the let's see, actually it's cosine theta 1. Okay, and delta D we know it actually is small r cosine theta 2. Okay, so basically this is the so-called S2 should be equals S2 should be equals R cosine theta 1 plus R cosine theta 2 cosine theta 1. Okay, Y2 should be equals R sine theta 1 plus R cosine theta 2 sine theta 1. Is that okay? That's it. And you use the different theta 1, theta 2, and theta 1, theta 2, and the G parameter. You can make a surface drawing, 3D surface drawing for the SYG, and you will get it. Any question?
I don't think so.
Okay, I'll give you the note, but eventually this solution, okay, the solution for this one, you have to write down the equation yourself, but the solution eventually will be like this, okay? And then if we plot it, this is the program. This is by some student 1 year before or 2 years before. Some student of the same class that taking the same class here, okay? So this workspace.plot. Okay, so basically he calculate different join number. Okay, so he used the 3D plotting. Okay, this one I believe I do have some example. You can try. You can actually look at the lab. Okay, you should have some lab you can leverage on. I'm gonna wait a little bit. Okay, so basically generate a different SYG. Okay, and then using the surface chart. Okay, using the X.plus surface and SYG, and then using some color plane, you should be able to apply it. Okay, you should be able to, let's wait for it. While we are waiting for it, let me actually look at this the modeling of the assignment. Okay. So the modeling portion, we just need you to write down the equation. Okay, I'm sorry. So here, basically, it describes the so-called SYZ equation, and then write down the equation in metric format. Is okay? And right here, he's assuming that the Z naught is actually 1. Assuming that Z naught is actually 1, okay? So, and big R and small r, they are some fixed number. Is that okay so far?
I think so.
Okay, so that's what I can give you. I can only show you this, but most of the student write down like it is a 2D planar robot. That's wrong. Okay, that's actually the wrong model. Okay, but we do need a solution like this. Okay, that's what I can tell you. But detail you have to figure it out. Okay, I can give you the note I have, but I don't know why this Louis Chet does not allow the attaching of the file. It does not allow the attaching of the file. I'm not sure. Okay, I'll send it after class. Let me do it this way. Let me actually send it by the message here, okay? So this one, basically, you need to model it first. And modeling it, the first thing is that you need to model the inner circle. I'm sorry, the bigger plane, bigger circle first. Because your second one is actually rotating according to the first one. Okay, this is programming assignment for nodes. Okay, let me actually attach those attachment to here. These are different nodes. Let me take a picture on this kinematic diagram as well. Okay. And this equation for your reference. Detail I don't want to give you. You have to figure it out. Okay. Detail you have to figure it out. Otherwise, we actually lose the purpose of studying. Okay. Any question? Any more question?
I don't think I have any more questions.
Yes.
Thank you.
Okay, no problem. There are students who copy the answer from each other. Okay. There are students trying to find the answer from previous year. I try my best to detect it to be fair among the students. But right now, the first few homework I did not actually penalize for those people who copy. Okay, but starting from this week, I start to penalize on those plagiarism or violation of the rule. Okay, I think that's not fair. If they continue to do that, that's actually totally not fair for other students. I have to actually make a clear statement that it is not welcome to do that. Okay, you're not taking away the chance for you to study, but also not fair for the people who actually work hard. So at this moment, I try my best to detect it. Okay. Okay, that's what I want to say because at this moment, we do see a lot of such problem. Okay, and next this week we are on the dynamic modeling. Okay, dynamic modeling, and then the so-called dynamic modeling is that we want to control the robot. Okay, so the so-called control is not just the actuator itself, not just the manipulator itself, but also including the feedback loop, and then using the feedback loop to optimize the control. We call it dynamic modeling. So this is the so-called dynamic modeling, and we can solve the differential equation by ODEINT, ordinary differential equation integration engine, set up by Python. Okay, and this the so-called dynamic system tool is extremely useful. Okay, extremely useful. So basically, any of the system, any of the financial system, any of the robot system, any of the equilibrium system, anything that needs to have a stabilization, anything that need to do optimization, anything that has a runtime balance, they all need to solve using this differential equation to solve it. Okay, and robot feedback loop is only one kind of a loop. Okay, only one kind of loop, and there are so many different kind of optimization. So this whole thing by itself, dynamic modeling by itself, is actually several classes, several courses. It's not just one. Okay, so what we can do right here is only to show you what is dynamic modeling, and then use the math when sometimes you need it. How can you solve it? Okay, how can you solve it? So basically, a dynamic system, you do have the open loop system and closed loop system. Okay, and this model can either be derived from empirical, the experimental or data-driven model, or from the fundamental math. Okay, fundamental relationship, the principle, the physics-based equations. So sometimes it's empirical, experimental, sometimes it's actually theoretical. Okay. And either way, you can build up your dynamics modeling. A combination of the two approaches sometimes is used because we are studying engineering, we are not studying science. Okay, science, you have to go to the fundamental reasoning of why the equation is true. Okay, engineering system, we sometimes get the so-called ad hoc solution. Okay, although sometimes we get the ad hoc solution. Sometimes we actually get empirical data to work. Okay, as long as it work, okay, it works. We engineers sometimes don't care about the theoretical background. Okay, that's called approximation solution or ad hoc solution. Okay, so first thing is need to set up the dynamic modeling. Okay, so there are charge conservation rule, there's a mass conservation rule, there are momentum conservation rule, there are concentration conservation rule. All kind of conservation rule would help you to set up a equation. A equals B, left side equals right side. That's the so-called conservation point, conservation. And based on the conservation, our system will go into the so-called a stable state. If your system cannot go into the system's stable state, then the system is unstable. The system is unstable. Your system may be diverging, and there's no convergence. Then it actually cannot control. So all of the purpose of the control system always is to try to find a dynamic system that can converge to a certain point. Okay, so these are charge conservation, mass conservation, momentum conservation, whatever conservation is very important because your input, so the whole system, usually including what? Including three parts. You have a tank. Your total water go into the tank minus the total water go out of the tank should be the same as the amount of water that you accumulate to the tank. Okay. The total thing that you accumulate should be the same as your total input minus the total output. That's the mass conservation, right? So based on the mass conservation rule, you should what? You should have the equation that you can set up. But if the system actually there's no feedback loop, is a water tank. You keep pulling the water. For example, if this water is actually 5 gallons per hour, but you are throwing out 10 gallons per hour, then what's the eventual level for the tank? It should get to 0, right? It should get to 0. So now, if my system right here, the input and output amount, okay, that's actually right here. Let's assume that my input right now actually is an X. My output is constantly 3. And my water level right here actually is, let's assume that here is 40 gallon. So now I want to set up this control system so that the water level would actually go to say 30. So if right here my current level is a gauge, if my current level actually is above 40, then what should I do? Here this one is fixed as 3, so my instilled water should drop. Then what happened? Then the water level would drop, right? And once it go below the 30, okay, go below the 30, okay, then I need to increase my infield so that you bring back to the equilibrium point. Is that okay? You hear me?
Yes.
So that's the kind of the balance or the kind of the control we want to have. Okay, you basically use a gauge to measure where it is. So if it's overshoot, you actually want to bring it back. Undershoot, you actually want to actually bring it down. Okay, so basically this is some kind of control, and we use the okay. There are 2 ways you can control it. One way is that if you have a fixed output, you control your input, right? If you have fixed input, you control your output. Either way, you can actually maintain your system to reach the balanced state. Okay, the balanced state. So this one, say here, this one is actually this is a dynamic system. Right now, we are talking about water level. So let's assume that here we do have a financial system for a country, right? Same thing. your money income to the company and the output to the expenses of the company is also a dynamic system, right? And how much cash reserve you need to maintain. It is a system that you need to actually make sure that you need to bring it to the healthy level, okay? If you do have extra cash and invest the extra cash, then your company's profit is not maximized, right? If you actually, your cash reserve level is too little, then what happened? You may actually facing a financial problem. So here, this financial system, you can also model it by the same tank theory to maintain a certain cash level. Is that okay? Hello, is that okay?
Yeah, I
Okay,
think so.
so that's what we say when you have a robot control system. It's not only used for robot. You can use that for finance system, any system as well. Okay, so that's actually the kind of things that we want you to learn. So there are steps that you want to do dynamic modeling, and you need to follow the guideline, and you will set up and you can do simulation. Okay, so the following guideline is for developing a dynamic model. So right here in our robot courses, you want to control your joint variables to a certain location so that you maintain your robot at a certain situation, certain configuration. Okay, so that actually is called a dynamic system. Okay, a dynamic system. So you need to identify the goal. Okay, the objective for the simulation. For example, you are driving a car. You want to maintain the same speed. That's called cruise control, right? Same speed, that's cruise control. So the objective is the same speed. If you want to actually accelerate, then the objective become the fixed acceleration, right? Is okay? So different objective will define the different goal for the dynamic system. And then once you actually set up the goal, you draw a system schematic diagram. So this schematic diagram will include in the kinematic diagram and its feedback system, and label the process variable. And this done all assumptions, determine the spatial dependence. Okay, and then find out whether you want to use the partial differential equation or ordinary differential equation, and write out the dynamic balance. So the dynamic balance should be is the mass conservation equation or species conservation, production, consuming, consumption balance. Okay. Any question? Hello, any question?
Oh, I don't think so. Sorry.
Okay, there's a background noise. Okay, it's okay. And other relationships such as thermal, say you have an air conditioner, you want to maintain at 70-degree F, okay? So those are the dynamic system you want to set up. Then you also need to consider there is a background disturbance. Okay, for example, you do have a window that's leaking your AC air, okay? So those are some environmental input you need to actually figure out, okay, and classify your output as state variable or control variable. So control variable, for example, using the AC's case, the control variable is your temperature, right? You want to use a temperature as control variable. Using the water tank level, the water level is of the total number of gallons is your control variable. So every dynamic system is a control variable that you need to maintain now. Okay. So when you set up your dynamic system, you need to take care of that. So case study number 1 is to fill a water tank. Okay. So you do have the input water, you do have a leaking outlet, okay, or something like that. So you need to actually your inflow mass speed, say scalar per second minus output speed is actually your net net mass transaction speed. Okay, that we call it the balance equation. Okay, and then you can actually calculate the density and whatever to translate the steel water flow to certain changeable volume. Okay. Okay, you set up your Euler semester and the ODR, set up the equation. Okay, hold it. And this water.py you can download from my system. Okay, the course you can download the sample code, and it will solve the problem. Okay, you can solve it. So eventually, it would show you that okay, different valve control, your tank level should be different. Okay, so you turn on your valve, here, then you start to put the water in. Okay, and then at a certain level, you turn off your valve. Then your tank level maintain a certain location, assuming that it's not leaking. Okay, not leaking any water out. Okay, so that it can actually solve it with the ordinary differential equation. And there's a toolkit so called Gecko. Okay, Gecko, you can get it. Okay. There's another one that actually you can set up this equation. And this one you can solve the problem. This one is decaying. Okay. Decaying. If you have a fixed decaying function and that decaying function is a function of time, okay, then your level should be like this, okay. Okay, so that's actually is a function, and you can also pass the function into the ordinary differential equation solvers, okay, and with different function, you will get different decay speed, okay. And you may have different model. So based on different model, you can come up with different dynamic system chart, okay? And this different chart right now, you don't see it, but later we will use it for the robot control, okay? For the robot control. Okay, balance equation. So balance equation is that your accumulation equals the in minus out plus generation minus consumption. Okay, in and out actually is your water input and the water output, right? But that's assuming that your tank is not consuming any water. Okay, it's not consuming any water. So you have an input and output, that's it. But sometimes say your water actually will evaporate. So they have consumption. Okay. And sometimes it actually would be getting more water. Okay, for example, your temperature drop down, the steam actually go back to water. Okay, so those are generation and consumption, not only in and out, but also generation and consumption will totally will be your accumulation. Is that okay so far? So
Yeah, I think so.
system equation actually is sometimes you have more variety. Okay. So anyway, here we do not try to teach you every single model, but they are species balance. They are actually momentum balance. The species based balance is usually for the what? When we are talking about an ecosystem, we do have tiger that will eat some small dog. Some small dog would eat some rabbit or okay, whatever. There's a food chain, right? There's a food chain. So who consume what? Okay, you can set up the equation as well and try to get a balance. Okay. Okay. Anyway, these are different equations that you can model. Okay. And right here, we don't have that much time to go through every system equations. Okay, we don't. But what I want to say is that whatever example we provide is a general mass modeling, and it can be applied to different application. Okay, and to us, when we study the robot, these different equations are used to what? To give you the idea of how the transition has been done. How fast can we control our system to reach the stable state? Okay. And we can also analyze it, and some of the differential equation you can also do linearization. Okay. Okay, these are math too difficult. I'm not going to repeat it. You can look at the video for it. Okay. So, and you can actually plot the plot. Okay, plot the plot about how the scenes get changed. Okay. Okay, here we do have several equations, so I don't go into this different detail. Each one of them, even the Laplace transform, if you really want to fully understand it, is almost the whole class need to be dedicated for it. Okay, so my portion today is just go over the overall idea of what we are doing right here. Okay, as for how to set up these equations, you can read these different notes and actually look at different problem case by case. Okay. Okay, I think today I'm going to talk to here. Any other question? And we don't go over the Laplace transform because actually it's take us hours to finish it. Okay. Any question?
I don't think so.
Okay. But if you do have question, let me know. Okay.
Okay.
So otherwise, that's it for today. Okay. So today's main purpose, I'm going over the basic idea of what is dynamic system and what to work on the modeling. Okay. I just give the key idea. And detailed equation, there's so many. Okay. So if I need to explain each of the equation, I think it's 1 hour, right? Every single one is would take a long time. Okay. And we do have some the lecture, we do have the pre-recorded video for you. Okay. And the sample code you can download. Okay. That's it for today. Thank you. Bye-bye. Bye-bye.
Bye. Thank you.